It's such an honor to be with you all here today to talk about this topic of pandemics or pandemics. When this panel and its mission was introduced to me, I was really intrigued because thinking about how integrated circuits and custom circuit design can help actually during a time of a pandemic, there are many different directions we could go with this conversation. We could talk about how computing is being used in high performance computing spaces to enable computation, which enables drug discovery, which enables us to more quickly determine root cause of the pandemic and the associated viruses. We could talk about how high performance computers, again, with custom processors and custom networking cards and lots of memory and lots of transistors in them, are being used to facilitate also, then drug discovery and vaccine discovery, et cetera. But I want to, in this talk a little bit more about kind of from the enterprise perspective of enterprise computing during a pandemic, what's been happening, what's behind the scenes in all of those changes in the way we as consumers behave, how that's driving certain computation and certain compute consumption, and then how that relates then to security, which relates back then actually at the end of the day into custom hardware design and ASICs. So I'm going to try to pull all those threads together as we go through this talk. My outline here is then to talk about what's happening during the pandemic, to sort of lift the cover on how digital transformation, other things have been changing in this era that we're in right now. Talk about how that relates to key concerns in data protection and data privacy, and talk about the role that custom ICs can actually play in ensuring data protection, ensuring data privacy, and ultimately securing cloud-based services and data in the cloud, which is very much where pandemic computing is heading. And then we're going to talk lastly about confidential computing and what does that mean? What are those technologies? And again, how does custom design and technology work play into that space? In terms of computing during a pandemic, across the globe, we have all each individually experienced that a lot of the way that we are living and working has dramatically changed in the last year. And there's a lot of questions about how much of those changes we'll continue to adopt. It's actually quite nice to get groceries delivered to your home if you live somewhere where that's a common thing that's happening. It's also nice to be able to do complete things like do your banking fully online and fully with apps on your phone and things like that. So across the world, companies are experiencing a lot of pressure to digitally transform. Everyone had to shift their workforce to be working remotely, but also be working securely remotely on a very short time scale. Those of us that work in technology, we were all equipped to work remotely, but not all professions and not all types of businesses were complete in that process in being able to enable a remote workforce. That's a digital shift. In addition, we all as consumers want to be able to end-to-end execute processes in our daily lives. Everything from the engineering work that we do to selling a product or a feature or function to someone to purchasing them something. Ideally you want to even be able to buy a house and have that entire transaction be performed digitally. Digital transformation is certainly about replacing paperwork and having there be more efficiency in transactions. But underneath the covers, there's a lot of computing changes actually that happen every time something moves from being non-digital to being digital. And so this has also resulted in a lot of changes in workload volumes. When we talk about computing, in a context like ISSCC, we're very focused on the throughput and the performance and the processor nodes and things like that. But all of those things get translated at the end of the day into compute workload that in many cases is facing consumers like ourselves. And there's been significant changes in workload volumes throughout the pandemic. We have all changed our behaviors. There's things that we do with the businesses that we engage with that we no longer do so much in person. There are other things that in our daily lives and in our engineering work we do completely remotely and completely virtually. And so at the back end of sort of all of the space of the world's ASICs and computers and such like that, there has indeed been a shift as to how much certain things are being used. And in some cases that's gone dramatically down, and in some cases it's gone dramatically up. I've gotten to work with clients that are looking at changes of X factors in the amount of sheer compute power and throughput that they need because of what's been happening in the pandemic. And so these ups and these downs point to what at sort of the workload or the computing level we refer to as elasticity, needing the ability to have a variable amount of compute throughput. And, yes, we work on processor designs and things like that enable people to, use threading to pack more compute onto the processors themselves. But at the end of the day, across the total number of processors and the complete compute capacity that's needed, a lot of elasticity is driven by the pandemic. And so actually all of this, including a need for greater cost efficiency in the current economic environment, et cetera, all of it really points toward traditional value propositions of cloud computing. And cloud computing is a particularly unique circumstance in that cloud is a place where there are a lot of people using the computing facilities, the data storage facilities, the network, et cetera. And when we start to talk then about cloud, it's important that we say, okay, cloud can be a place where we can realize that elasticity, where we can realize the digital transformation, but what are sort of the guardrails? What are the new first-class design considerations that come about when computing is going to be deployed in a cloud context? In this conversation around the pandemic, the reason that this relates together is that the drive for elasticity, the drive for new workload is actually driving significant new adoption of cloud. But the current environment is also driving a lot of conversations around security, around protecting workloads and then protecting them in particular when they're running in a cloud environment. A couple of keywords that we're going to be talking through in the next couple of minutes include encryption, isolation, ensuring that things can kind of compute in a secure and comfortable enclave and environment, and being able to protect data when it is at rest, meaning encrypted and stored on a storage facility, and there are keys that protect that cryptographically protected data. There are keys, that are used in the encryption and decryption of that data, and protection of data in motion, which requires doing a lot of cryptography throughout the system itself. Confidential computing is a particular definition that's driven by a consortium these days, but confidential computing is the desire or the technical capability to enable the user of a computing environment to have full privacy and authority over what they're running, over the code, over the data, even when they're working in an environment which is effectively shared. So in a shared environment like a cloud, confidential computing can enable someone to effectively technologically ensure that they have the isolation and privacy and data protection that they need to be very comfortable that they can compute in the cloud with confidence. So to jump down a couple of different layers and sort of get closer to the heart of where ISSCC and its audience is, I want to talk a little bit for a few minutes about hardware security modules, some things about cryptography technology, and how we actually design tamper-proof hardware security modules that then feed into unique characteristics around data protection and data privacy in the midst of cloud computing. First concept here is a secure hardware security module, or secure HSM. A secure HSM has to be a general purpose computing environment, meaning that the overall design of the ASIC and the associated peripherals have to enable a variety of different types of computation. Yes, cryptography, yes, a number of different things, but a general purpose computing environment that has to be able to withstand both physical and logical attacks. And when we're talking about wanting to be computing in an environment with confidence, both are actually really important. The device of a secure hardware security module has to be able to effectively, run with confidence the software that it's supposed to be able to run, and you have to be able to distinguish as to whether or not what you are looking at is a device that's appropriately configured and original and authentic, or someone that's trying to mimic that. When we talk about hardware security module, it's also really important for a secure HSM to remain secure even if someone tries to carry out a destructive analysis of that hardware security module. What I mean is that when it's designed, you need to be able to detect tampering as well as take action actually if the card or the ASICs or any component of the overall device was tampered with. When you can ensure that you can handle any sort of tampering, not only detect it, but take action to protect the contents of the ASIC and the hardware security module, you've significantly raised the level of trust, because not only do you know then that the card and its contents are safe and secure, a lot of isolation, other things like that are happening, but you know that, for example, if anyone tried to walk off with this capability physically, they wouldn't be able to later decrypt interesting data or be able to otherwise determine the contents. This is key to being able to secure the storage of keys in a cloud environment. Specifically, keys are sort of that decoder ring that enable protection of data when it's been encrypted on a cloud. Being able to secure keys on a card that effectively sort of self-destructs and it zeroes out if tampered with chemically, physically, etc., enables people to know that even their keys can't walk out the door of the cloud. Cryptography is a really important aspect overall of secure processing and secure processing in a cloud. And it's important that the hardware security module itself have a large amount of cryptographic throughput in order to be a high performance engine of cloud computing. The 4769 hardware security module is a custom hardware module that actually has those characteristics that I laid out previously as sort of that definition of having a secure HSM. So it has tamper sensing, but then it also responds to tampering and zeroes out the contents of the adapter. It has a large amount of cryptographic throughput, as well as the ability to support a lot of logically separate cryptographic domains, up to about 1,300 as a matter of fact. That scale, that elasticity, the ability to support lots and lots of users goes all the way down into the design of the transistors, the design of the card, etc. And it's important to have that high volume of throughput, that high degree of partitionability in order to be able to support computing in a shared environment like a cloud. When we look at the ASIC inside of it, this is just a high-level diagram, but certainly necessary for conversation at ISSCC. There's two blocks that are highlighted in this picture. One, the crypto engines, and there are 12 public key and modular math units on the processor, on the ASIC, excuse me. Down in the processor complex, there are 4 processor cores running at 1.2 gigahertz. And there are a lot of different capabilities on this ASIC. There's a symmetric key unit, a true random number generator, a deterministic random number generator, all of those core capabilities and functions that are needed for cryptography and for supporting many, many different types of standards. And supporting lots of different types of cryptography and such is also important when talking about cloud computing, because increasingly people are starting to wonder, if I am doing computing somewhere, what if at some point in the future, the information that I have, stored in that off-premises location in that cloud could be decrypted using a quantum computer as an example. And so deployment also of quantum secure cryptography is something that's also important to be looking for in a cloud in order to ensure that the cryptographic algorithms that are in use can be robust against the next 10, 20 years of quantum computing capabilities. And so I want to just for a minute here bring it back to, what does this all have to do with a pandemic? The thread that I was trying to pull through in this last 10, 15 minutes here was to describe that custom hardware, custom ASIC design, high performance cryptography throughput, support of many different cryptographic standards. A custom ASIC can be the basis for a high performance secure hardware security module design. A secure HSM can be combined as a hardware component with software components in the system that implement secure enclave technology. Together, these can form the basis for key services that enable protection of data, things like key protection services that enable keys to be protected in an enclave such that not even cloud administrators could get access to them. This type of technology can be used to run substantial workloads as well within the confidential computing paradigm because of the isolation, because of the throughput, because of the tight integration between the hardware and the software. And so workloads of even 16 terabytes in memory footprint size, really substantial workloads through this end-to-end design, all the way down from the transistors of the hardware through the system software stack and ultimately the cloud delivered services, can enable confidential computing where the workload runs in a cloud with those value propositions of elasticity, cost flexibility, and overall in a modernized context and a digitally transformed context, things can run in the cloud, but people can have confidence that the data is protected, the keys that encrypt the data are protected, that the entire compute itself is protected and isolated, even though the cloud is a shared environment. And there's great economic benefit, there's elasticity benefit, et cetera, to being in a cloud, and to be able to isolate things through design that goes all the way down into the transistors is a great opportunity for people to respond to the economic environment, respond to the change in consumer behaviors, and respond to the changes in enterprise workload demands of a pandemic. So hopefully this gave you a little bit of an idea of how we pull the thread all the way from custom design, encryption, design all the way down into the transistors, up through system software and cloud delivered services to give people confidence that they can compute in a cloud when cloud is really what they need to do in a time of such high volatility.